Well, lately, when it comes to antennas for amateur radio operators, end-fed antennas are being used a lot. These antennas are fed at one end and require a transformer. In this video, we're going to talk about the materials we can use to make these transformers, which generally use a ferrite ferromagnetic core. Ferrite, here you can see there are a few cores of this type. Some are toroidal, others are square. Well, there are all kinds, right? But they're of this type. It turns out that these cores are not all the same. They look like they're made of the same material, but they're not. They're made of different compositions, and not all of them are suitable for making these radio frequency transformers. So don't just use any random thing because it might not work for you. Well, in this video, we're going to see how to identify if the core we have is suitable or not for a matching transformer. One of the parameters we'll look at is the relative permeability. This parameter tells us a bit about how much inductance a coil will have on this core, right? For each turn, what inductance will it have? The higher the permeability, the fewer turns the coil needs on the core, right? To make this measurement, we're going to use the NanoVNA or an inductance meter as well. Well, you can use any of the methods I showed you in this video that's up here in the eye. And we're also going to use some tables from a manufacturer who makes this type of material that's used to make the cores, right? And we're going to see how these materials respond to different frequencies. If the cores are round, like toroids, like these for example, you can use a calculator that's on the same page. I'll leave the manufacturer's link below the video, and we'll also get the table of core characteristics from there. Depending on the material they're made of, they have an identification number. Well, we'll be able to identify them with that number and see the response at different frequencies. But since we have cores of different shapes, well, we'll use artificial intelligence to do the calculations for us, as I'll explain to you in a moment. We'll start by measuring the inductance of a few turns of wire on the core. As an example, I'm going to use this core, which is square and comes from an old flyback, and to measure the inductance, I'm going to use the NanoVNA. You can use an inductance meter if you have one. I'm going to do it with the Nano because later on, I'm also going to use it to see the core's response over a range of frequencies. And is what this manufacturer's data tables show us actually true? As I told you, I'm going to use this core from a flyback. I'm going to wind 10 turns of wire on it. You can use any number of turns. You can do 5, but well, I'm going to do 10. And you have to write down that information, the number of turns we're going to make. We'll measure the inductance with the Nano. Well, so this is something we're going to display. Trace. We choose the Smith chart. Now format, again, we choose Smith, and in Smith we choose R plus LC, L over C. Now we move the mark to the lowest end of the frequency range, and at the top we'll get a direct inductance reading. In this case, the value is 40.7 microhenries. So right next to where we wrote down the number of turns, we also write down the inductance value we get. Now we're going to take the measurements of the core. In this case, since it's a rectangle with an inner window, we're going to measure the outer perimeter. For that, we add up the length of all 4 sides. In this case, we can measure 2 sides and multiply by 2. One side measures 59, the other measures 54.5, and multiplying that by 2 gives us 227 millimeters of outer perimeter. Now we're going to do the same with the inner perimeter. We measure two sides and multiply by 2. In this case, it's 37.5 plus 35, all times 2. In this case, we get 145 millimeters of inner perimeter. We also measure the height of the core, which is 11 millimeters. We write down all this information. And with all this, we go to ChatGPT or Gemini, whichever you prefer, and we enter the following prompt. Calculate the permeability of a ferrite core that, with 10 turns, has an inductance of 40.7 microhenries. It has a frame shape. The outer perimeter is 227 millimeters, and the inner window perimeter is 145 millimeters. And it has a height of 11 millimeters. Well, once we enter all that into the prompt, we press enter and wait a bit because it will process. And it will also give us the whole series of formulas it uses to make the calculation. So it's not just that it gives us the number, and that's it. If you want to learn more about the formulas and all that, well, it will give them to you there. It will give you all the formulas it uses, how it does the calculations, with the measurements, with the units, and all that. Well, here it has already given me the relative permeability, which in this case is 267. What's that? That's the relative permeability. It's a number that doesn't have units, precisely because it's relative. If it were absolute, it would be in henries per meter. With that permeability, now we go to the Ferrite materials table from Ferrite, which is the manufacturer I mentioned that has all the data. Okay, here you have the table. Below, I leave you the direct link to where the table is. Let's see which material this permeability could correspond to. And if we look, we see that it corresponds to material 52. According to this table, it's telling us that the material with a permeability around 300, or the one closest to the 267 this core has, is material 52. Well, also, right there, if we keep going down under the column for material number 52, we can also see the recommended frequency range for this material. According to what it says here, less than 20 MHz, less than 20 MHz. Well, to confirm this, I have assembled a 1:9 transformer with this same core that we have measured. I'm not going to explain here how it's done. These balance, these transformers. If there's interest, I'll cover it in another video. I'm going to put a load on it, a 475 ohm resistor. Actually, it should be 450 because 50 times 9 gives me 450, right? But well, since I don't have that value, I'll use the 475 1, and I connect the NanoVNA to the input of the transformer. Let's go to stimulus. We set it from 1 mH up to the stop. We set it at 30 MHz Gers. Now display SWR format, SWR, we go back to display, scale, show grid. So it shows us on the side the SWR value we have at each point, at each frequency. And now we see the curve that matches exactly what the table showed. Starting from 20 MHz, you can see that it starts to rise and it doesn't work as well anymore. However, for the lower bands up to 20 MHz, it works quite well. And in practice, I can tell you it works well. Because I have a transformer made with one of these cores on an antenna with which I have made excellent contacts. On the 40 20 and 15 meter bands well, the same goes for the transformer working well and giving us a good reading. Low SWR across that whole frequency range doesn't mean that when we attach the wire, I'm going to have that acceptable SWR across the whole range from 1 to 20. Because the antenna, the wire, the one we're going to feed there on the side, is not going to present an impedance of 450 ohms across all the bands. But that varies. And because of that, it varies too. This type of antenna, which is called end-fed, needs a tuner at the transmitter. Not only this transformer, but also a tuner to further reduce the SWR, right? Well, I haven't said anything about the power to use with these cores either, because you have to see how they behave in practice, whether the core heats up or not. I'm using it with 50 watts and there's no problem, but with more, you have to test it. Before putting a kilowatt into it, run some tests with 100 watts in FM for a while and see if the core heats up. If you're going to use cores made of material 43, for example, or any of those expensive ones, run the tests beforehand. About the heating issue, because when these materials get hot, they lose their characteristics, right? So it's not a good idea to, put a kilowatt through one of those and wreck it because these cores are expensive, right? Well, before you go, please subscribe to the channel and share it on your social media. That helps me a lot. Please give it a like. Thanks for watching the video. See you next time, God willing.